Hello, everybody. In this recording, I will go over the runtime analysis with you. I try to record my lectures in small segments. That way you can view per topic and it's easier for you to follow along. So let's talk about runtime analysis, some of which you have been exposed to on your earlier programming classes. By all means, this isn't the only time we're going to talk about runtime analysis. We're going to go into code analysis pretty soon, and we're going to be talking in more details what it means to have a runtime analysis given algorithm. So the general question that we have to ask ourselves is, what does it mean for any data structure that you may end up using in future to perform slowly or perform really fast? What does it mean to have a slow or fast algorithm? How do we measure that slowness or fastness? What kind of metric do we use? Do we just look at the computer wall clock time and say, oh yeah, it ran in 3 milliseconds, we're good? So how do we define that goodness, right? And just looking at the computer wall clock time is not going to help us determine the goodness of our algorithm, fastness or the slowness of our algorithm. We look at it differently. So why do we not pay attention to our computer clock? Well, first of all, depending on what type of computer you and I have, it will affect the outcome. So the different hardware will end up with a different speed result. So if I happen to have the newest laptop and then you happen to have 3 or 4 years old laptop that the processor is relatively older than mine, your clock time and my clock time are going to vary. So that is not going to be a fair assessment of our algorithm if it's actually slow or fast. It also depends if we are looking at our computer, just depending our slowness and fastness to our hardware equipment. It also depends what other programs are you currently running while you're executing this program. So those are not good measures for us to use in order to determine the slowness or fastness. The other thing that will affect the speed of your algorithm is the size of your input and, most importantly, type of your input. That is something we are going to focus more when we talk about code analysis, but that is going to be staying in your mind. So what we have to do is then, in order to come up with a general approach to define the slowness or fastness of our algorithm, we look at a particular algorithm and we count how many steps a program that you have written, the algorithm that you have written, takes to execute on a given input size. Let's call that n. How does it do? How does it perform? Okay. So basically, this may have been visited very generally in your earlier programming classes. Usually it's in second object-oriented programming language class. It's, 231 is considered to be object-oriented 1, 232 considered to be object-oriented 2 at MSU. And if you're coming from a similar background, that's pretty much your later object-oriented programming class where they just cover it in general, what it means to have efficient algorithm, very general terms. So the efficiency that we are going to pay attention in this class is going to be measured by what resources your code is using and how much of it it's using. For example, how much space it's taking when it's running, how much memory it's taking when it's running. That is known as the space complexity, something we will talk about, and then eventually we will make it part of our project requirements. Efficiency is most importantly measured as the time it takes for that algorithm to run given a particular input size. So that's how we measure the efficiency, by looking at the runtime, looking at the space and memory complexity. And another important area that we focus on when we are measuring the runtime, it is its behavior as the input size changes. How does your algorithm behave as you increase your input size? Is it slowing down? Is it taking longer to compute? If you tested your algorithm to 100 element versus 1 million element, did the speed change? Did the time that it takes change significantly? That it caused you to raise your eyebrows and say, oh no, this is taking too long for a large input. So efficiency is going to be depending on the size of the input as well as the type of the input. The size of the input can be something you can eventually control. Maybe you will use your program for a particular input size, no more than 10,000. My algorithm is really good. It behaves really well, fast, or whatever measurement we're going to define it as. It's going to be a good algorithm as long as the input size is less than 10,000. But if I exceed that, it starts slowing down. So that is the size. And then the type of the input. Type of the input you cannot control really. Whatever you're getting for your software product, you're receiving it from your client, and that's the type of input they have. Say, for example, you're working for a bank account or some sort of a stock market program. You cannot change the type of the input. That's what you get. And how is your algorithm is behaving in terms of a random input versus somewhat sorted input? Those are going to matter in order for us to create the efficiency description for our algorithm. So what are we going to assume when we look at an algorithm? In order to look into runtime analysis, we are going to assume that every Python statement takes the same amount of time to run, just to eliminate a lot of little details. They are not going to matter at the end. I'm going to teach you how we are going to look at that, but we're going to assume every Python statement takes the same amount of time. And we are going to assume method call runtime is the total of statements in its body. How we are going to determine the efficiency of that method is what's inside of the function's body. We are going to assume loop runtime is number of repetitions times the total of its body. So let me give you general examples. These are, look at it like a pseudocode from your previous programming languages. They are not looking like Python, and you're right. Imagine that in your earlier programming classes, in your object-oriented programming classes, you have dealt with statements like this. Assignment statements, such as variable A is assigned to B plus 1. Or you have written a simple loop, and the loop was going through the entire input size n in this case. And the value was assigned to an array in your code. Or you ended up writing a nested loop. Outer loop is going as far as the input size. Inner loop is going as far as the input size. And then vaguely, you may have talked about this in your earlier classes, that assignment statement, something like that, grows or runs in constant time. You can say 1 millisecond, 2 millisecond, it's constant. We don't really care. That's why we call it constant. This is going to run depending on the input size n, right? If you had it n equal to 10, this loop is going to run 10 times. At the 11th time, it kicks out. So it grows linearly. For every input that you're processing with, the array is loaded with a data, right? And this is going to run in quadratic time, because the inside of your loop, for every one time the outer loop runs the inside of your loop, the second loop, nested loop, is going to run n times. So inner loop runs n time, the outer loop is going to run n time. N times n is quadratic. So pretty much that's where you were exposed in terms of your programming and defining perhaps what they look like, and use the terminology of big O to define its fastness. Now we're going to go a little deeper than that, but I wanted to give you the basic understanding of the goodness of your algorithm is measured with these growth functions. To be exact, in this case, we are using the big O notation. So for the constant that I showed you as an example, A equals A is assigned to B plus 1, that is considered as constant. Even if you increase the data size, it doesn't depend on the size of the input. It's never going to change. The runtime for that statement is never going to change. That's considered to be constant. We refer it as big O of 1. and increases slightly as the input increases. So number of elements are increasing. The runtime for that algorithm increases very slightly, which is ideal for a lot of the algorithms that we write. We try to aim for log n, and the runtime increases very slightly, meaning that as you increase the input to 10 to 1000 to 1 million, the runtime hardly ever changes. So that's a very good outcome for an algorithm that you have written. That's called log base 2 of n. Everything we talk about in this class is log base 2 unless it's specified otherwise by me. So, and then as you increase the input size, say to 10, to 100, to 1000, the time that it takes for that algorithm doubles. That is known as linear big O of n. Take a look at how it grows. That's something you may have discussed in your earlier programming classes. Doesn't matter. I go over it again and again in this class, so nothing to panic about. And then another ideal domain that we like is n log n. If I cannot write an algorithm that will grow linearly, like using perhaps a simple loop, I couldn't do something repetitive that will grow linearly. But the best thing I could do was to be able to write an algorithm that grows slightly more than doubling, slightly bigger than big O of n, which is n log n. That still is in the fairly good domain. And then as it gets, the big O time increases to quadratic 2 to the n, runtime will increase dramatically. So take a look at your runtime big O of n squared, big O of 2 to the n, and n factorial. Those are horrible. So I kind of color coded so you can actually see that. So those are going to be referred as growth functions. In this case, we are using particularly the big O. I'm going to go into details more as I describe you the code analysis and then the growth functions. But right now, I'm just simply introducing it to you what it means to have these category to determine the efficiency of your algorithm. So a lot of the times, what we do is we use this runtime analysis to help us. And then in our class, we define what's a runtime analysis. We go over code analysis. We're going to discuss recursion. And then eventually, what we're going to do is once we finish these fundamentals, we're going to go from one data structure to another, one ADT to another. So let's talk about what it means to work with ADTs. ADT is short for abstract data type. And basically, in an abstract data type, it is a data type that does not specify any one implementation. It's about what is provided as opposed to how it's provided. So it will tell you in general what would be its behavior. So for example, you can create a list. You can use a Python's list to create a list or a linked list to create a list. But list is going to be an ADT. And Python's list is a built-in container. I will refer to it as container in my classes, something that you will use to build these abstract data types. Or you decided not to use a Python's list, you decide to use a linked list. You're going to use perhaps Python's collections class to import the linked list. It already exists. And then using linked list to build a list class. Or you're going to write your own linked list, like in our projects that we're going to give you. Your first project, for example, is going to be you working on a doubly linked list, right? So these are going to help you, these containers, they themselves are considered as ADTs, by the way, is going to help you to build more complex abstract data types. So it is not how, it is what is capable of doing. So what can we do to take advantage of these ADTs? You're going to find out, for example, in order for you to build a stack ADT or a queue ADT, which is something we're going to talk about, we haven't covered that yet, you're going to perhaps use a resizable array or a Python's list. Or you're not going to use a Python's list. You're going to say, you know what? I'm going to use a doubly linked list to build a queue, or a singly linked list to build a stack, or I'm going to use a doubly linked list to build a priority queue. So stack, queue, priority queue, trees, these are all abstract data types that you are going to build using either a Python's list or a linked list. which is at the fundamental level that you're choosing one of these structures to build more complex abstract data types. So let's take a look at Python's list. What is it there that it can offer to us? Well, Python's list is a collection. It's you will see me refer it a lot like a container, and same as you saw in your Java or C++ class as array lists. It's a container. It's a collection where you can add elements in an ordered sequence. You can access to each item using its index. You can add and remove from various positions in your container. You can check if it's empty or not, right? And so these are essential what it's capable of doing, what it is able to offer you. So I show you a couple of Python's list declarations. There are various ways of declaring it. If you are feeling a little rusty, and if you have the opportunity to purchase Zybooks, you can take a look at the Python chapters where you're practicing with lists. If not, you can Google some of the Pythons. How do I create a Python's list? How do I go over a list? How do I iterate a list? Those essential skills, make sure to revisit them. So let me show you different implementations. What is given to you if I choose to use a Python's list? Python's list is an abstract data type that was built within the language. So whoever wrote, the team of people who created Python language, created this built-in container for us. What is it capable of doing? Remember, ADT answers to what, not how. It is able to give us the functionality for adding a value to the tail end, inserting a value at any position we like, being able to remove it from the end of the list or the beginning of the list if we specify the index, right? Being able to delete or remove an item at a particular location. Being able to remove just simply looking for the value. So it has that built-in search function to look for the value and then remove it from the list. And also copying from one list to another list, so on and so forth. You can even sort it. So in reality, for visualization reasons, this is what your list will look like. It is dynamically grown. That's what the Python's list is capable of doing. Array list is what you learned in Java or C++, has some functionalities as well. Be able to return the index of your data, set the data to a certain value at that particular index, being able to add, being able to remove, being able to report to size, so on and so forth. Array lists, however, has a little bit different structure than Python's list, because when you instantiate an array list in Java or C++, you have an initial size, default capacity. I believe it's 10 for Java, but you should Google that and find that out. It's been a while I haven't used Java. So what it does is it has an initial capacity, and then it adds it to the front of the list and then builds it. Just keep adding the incoming element. So the next element is going to come. It's going to go to the third index, the fourth index. Once that free space is filled, dynamically changes its size, doubles it up, and then same thing. But it's always a fixed number amount that is being allocated in the memory. So linked lists, however, another ADT, you get to choose between a Python's list or a linked list that you can use to build more complicated data structures, where you can write your linked list as a singly linked list, doubly linked list. Here's an example of a singly linked list where you have a reference to the next node, the next node, the next node, so on and so forth. So you should be able to add to the beginning, add to the end, add anywhere by traversing the list, be able to report if the list is empty, be able to remove anywhere in your list, so on and so forth. So you can add these functionalities if you choose to implement it yourselves. Excuse me, my phone just fell down here. All right. So that's that. What I did is, try to keep you engaged in the lectures. I'm using this semester a tool called Item Pool. I put these locations on D2L. So at this point, you should be able to pause the video, go to this link, and answer a couple of questions regarding what I have covered so far. that will kind of help you understand what we're talking about, and it will also encourage you to revisit the concepts. So I'm hoping that you're going to check this link and answer a few questions that I had, just two questions that I asked you about runtime analysis. So next thing that we are going to focus in this class is the design analysis. So for every abstract data type that we are going to go and talk about, cover, there are different ways to implement. There isn't only one way to implement. So what should you be looking at as a software engineer? You should be looking at, depending on which fundamentals you choose to go with, either using a Python's list to build a more complicated data structure or a linked list to build a complicated data structure. How long does it take for your algorithm to run? How much of the memory you're using? How is your reusability? Because object-oriented programming is created for one more very big important reason, that reusability. Is it what you created is something that's reusable, right? And consider writing one function efficiency compared versus another. Where is your function standing? How robust is this? When you release this on different platform, how is it behaving? So those are going to affect your design decisions, okay? And hopefully that you will make the right decision. So a lot of the times, since this is the class that's being used for you to get your internships or your jobs in future, it's one of the interview questions. What type of data structure ADT should you use to solve a particular problem? So hopefully by the end of this class, you are going to be exposed to enough ADTs to decide which data structure would be perfect for you to use to solve a particular problem. That's the reason why you're taking 331, to write better algorithms, to make the right calls, choosing which data structure to work with. So here's a design decision for you. Say you have some local restaurant. They wanted you to actually implement a new system in order to take their orders. So when an order comes in, it's placed at the end of the set of orders. And the food that the customers are about to receive is prepared in approximately the same order it was requested. But sometimes orders are fulfilled out of order. So what implementation should you use and why? Be able to explain it to me what you're going for and why would be the case, right? So if, for example, you choose to use Python's list, creating a new order is super easy. As long as I don't have to resize. We're going to talk about that when we talk about stacks. As soon as I decide to resize, that means the input size changed from 500. Originally, it was 500 to 1,000, say, for example. In that case, I have to change the size of my Python's list. I have to double up, and that will change the efficiency, runtime efficiency. We will talk more about that. And cooks can see any order at any given time very easily. If I choose to implement this particular problem using a Python's list, those are my pros. How about if I choose to implement this particular problem using a linked list? Um, Creating an order is slower because I have to iterate through the whole entire linked list. But the removing an item is going to be super easy because I'm going to be removing from the front of the list. You're going to say, well, you can easily remove Python's list from the front of the list by simply referring to the zeroth index. Yes, you can, but it's going to change the efficiency because everybody has to shift by one element up to the zeroth index to fill in that hole. We're going to talk about that more. And that will cause a linear operation. So it will increase your runtime. That is not something you desire. So what you're going to do then, in order for you to decide what should I go, which structure, which ADT I should use to build and solve a particular problem given to me, create a pros and cons list. If I use Python's list, what is the cost for me to add an item to the front of my list? Uh, Again, you're using the zeroth index, and if you do insert at the zeroth index, there's going to be shifting involved, and that costs linear time. As opposed to in a linked list, you can always just change the reference to head to just point to the new incoming node. Therefore, that's done in constant time. Removing an element from the front for a Python's list is going to cost you linear time because you're removing something from the zeroth index. Again, shifting needs to happen to fill out that zeroth index hole. You just removed an element, there's null. You have to shift everybody up by one to fill that hole. And removing from the front is constant in a linked list. Adding it to the back. Now, adding it to the back is constant time in Python because you're just simply adding it and there is no shifting involved. However, adding it to the back may cause, depending on what type of linked list you're using, by the way, this is a single linked list with a head reference, so that may cost you linear time. If it's a doubly linked list or if it's a linked list with a head and a tail, that complexity may change, assuming you had a single linked list with a head reference. Removing from the back, again, is going to be linear in a linked list, depending on the type of the linked list you use. The reason we give you your first project as a doubly linked list because that tends to be the most efficient. So singly linked lists are not to be that efficient in terms of runtime when it comes to these essential operations. So get item, put item, similar idea. So that is going to help you decide which structure you should be choosing to solve a particular problem. So it is actually our job to be able to clearly look at the list and deciding on a design. So the evaluation part of where you're creating pros and cons is going to lead you to the correct structure. From that point on, using that structure, you're going to solve a particular problem. For this lecture, like I said, item pool link is existing. And I also put the link at the end of my slides. So if you go to lecture slides on D12, you'll find these links. It's user friendly. Click on it. Make sure to answer these two questions to help you, assess yourselves how much of the discussion you actually understood. Thanks for listening. I see you next time.